with you next week in case that we need to do a bit of revision for you. Yeah, although probably not really necessary because this semester we don't have any final exam, but we have the assignment and we will do the assignment in week 14. Yeah, next week we will do the assignment. Yeah, any questions? So we look now at what I will discuss with you for this week. So we have basically I've covered with you on the control, yeah, control terminology, and then analytical modeling, Laplace transform, and of course one lecture on analytical modeling. In case you cannot follow that, you can listen to that um, analytical modeling class, and then transfer functions on YouTube, yeah, and then feedback control systems. We discussed it um, last week, and also we have learned about dynamic control systems. Yeah, I put it in topic 14 here, as well as control system design last Friday. Yeah. So for today, because you do not have group presentations on the group assignment, yeah, so I will uh, basically present to you what actually means with control system design. Yeah, that we covered for so which we did last Friday. So for today, we just look into the final lecture on overview on instrumentations control systems. This one here. Yeah. So you have to look into these notes also earlier this semester before we take a break due to MCO. Yeah. So we look into this again today as our final lecture. Yeah. You cannot see it. Let me see again. Okay. Yeah, I need to refresh it every time I change the application. Now you can see, right? I believe you can see it now. Yes, great. So this is will be my final lecture on control systems. Yeah, where we look back into the instrumentation. Yeah. So next week, uh, I will ask Dr. Fikri to take over again in case he wants to discuss other things with you. Yeah. So we look into um, a typical process transducers in a control system instrumentations. Why I want to repeat this one because I noticed that some of you are still confused. What is the difference between sensor and transmitter? Yeah. Actually, a sensor and also a transmitter is actually um, the content of a transducer. Yeah. So a sensing element will sense what you want to measure. For example, you want to measure a temperature, for example. Yeah. So what kind of instruments do you use to measure temperature? Yeah. You can use thermometer if a liquid. Yeah. But if let's say the temperature is very high, in that case you can just use a thermometer, which is normally made of glass with mercury inside that glass. Yeah. Or capillary. So in this case, you need to use a metal to measure the temperature. So the heat that will go across the medium where you measure, yeah, and arrive at the surface of the metal will give you the temperature measurement. So in this case, the metal of this which is the makeup of this thermocouple actually the sensing elements, the sensors. So they call it the sensing elements. Yeah? and the temperature will involve or will produce electrical current inside this thermocouple, yeah, and the thermocouple normally we connected to a computer, yeah. It will give you a reading of that temperature based on the electrical current that is produced due to the temperature, and that is actually the process of transmitting um, the signal or generator produced by this temperature measurement by the thermocouple. Yeah. So we have sensing, and then we also have the transmitter. So basically, the sensing element and transmitter is actually the component of a transducer. Yeah. So in this case, each of the transducer we have is on. If talking about modeling, this is on mathematical modeling, and therefore it's on transfer functions. Yeah. So we have the measured quantity of the process variable measured by that particular transducer. Yeah, based on what kind of sensing element is being installed, is the temperature, it could be a thermocouple or a thermometer. Yeah, and then it being transmitted to the computer. So it's called the transmitter. Yeah, and then the transmitter basically transmit the signal to a computer or to a controller in this case. Yeah? So that's basically what it means with a transducer. Yeah, so a typical process transducer. Yeah? So this figure 9.3 basically illustrates the general configurations of a measurement transducer, and it typically consists of a sensing element combined with a driving element or the transmitter in this case. So this actually leads to the what's called electronic instrumentation, because we have a sensor which we actually sensing the measurements or the variables that you have to measure, and then the transmitter inside the transmitter will transmit the signal, which is normally electrical signal, electrical current, yeah, to a computer, and that is basically considered as the electronic instrumentation. Electronic because its size is small in this case. Yeah, we're talking about the size of a diode, for example. So it's electronics. Electronics. So this is already being done since 1960s. Yeah, and by now 2020 is already widespread. Yeah? Not only that, probably you also come across words like uh, micro controller, for example. Yeah, and even now we have um, come across the word nano technology as well. Yeah, so that is um, how spread it is now since 1960 until now. Yeah, things getting smaller and smaller. Yeah? So it's not surprised that in 1990, for example, where most of you 1990, I think most of you not check born. Yeah, um, the size of phone, for example, is probably the size of your school bag. Yeah, but by now, the most advanced handphone no longer called handphone, but called a smartphone, probably as big as um, a box of matches, for example. Even someone you probably never seen a box of matches anymore. Yeah, because people now do not use matches. Yeah? Instead, they use a lighter, for example. Yeah. So this is how it evolved. Yeah. So basically, um, you need to understand by now. You need to understand what is actually meant to sensor and a transmitter. Yeah. So in this case, in this last lecture on uh, instrumentation for control systems, you want to review back what are the most commonly used sensors for the most important process variables. Yeah, and also understanding what it means with transmitter. Yeah, so if you look first into transmitter, what actually meant with transmitter? Yeah? A transmitter usually converts the sensor output to a signal label appropriate for input to a controller. Yeah, so talking about electrical current. Yeah, and the current could be as low as a 4 to 20 milliampere. Yeah, and a transmitter are generally designed to be direct acting. Yeah? And in addition, direct acting means is connected directly to the computer. Yeah, although now with the advancement in communication technology, Wi-Fi probably or Bluetooth probably being used as well to transmit the signal. Yeah. So in addition, most commercial transmitters have an adjustable input range or span. Yeah. So if you measure a temperature of boiling water, for example, you know that it could be one maximum 100 degrees Celsius, for example. So in this case, you need to have uh, an instrument that can measure from 0 to probably to 110 maybe. Why? Because we know that the limit is around that 100 degrees Celsius. So for example, a temperature transmitter might be adjusted so that the input range of a platinum resistant element or the sensor is between 50 to 150 degrees Celsius. Yeah? There's examples. Yeah? So now we look into the many types of online measurement options for process control for each of the variables that we discussed in the past 11 weeks. Yeah? Of lecture, although longer than it, when we consider the MCO. Yeah. So variables like temperature, flow, pressure, level, and the compositions of applied measurements also being considered. Yeah. So for temperature, for example, it started with a thermocouple. Yeah. So by now, I think you well aware the structure of a thermocouple. Basically, it's a combination of two wire of different property. Yeah. Different types. Yeah. So the difference in flow is giving you the reading. Yeah. And for temperature also we have resistant temperature detector or RTD or field system thermometer. We are using a mercury thermometer or sometimes we use spirit also. And we have bimetal thermometer. Yeah, the concept similar to thermocouple. Then pyrometer, which is based on total radiation, photoelectric, and the ratio. And then we also have temperature measurement with by using laser. Yeah. And surface acoustic wave as well as some of the semiconductor, yeah, like diodes, etc. This for temperature. As for flow, we have orifice meter, venturimeter, rotameter, yeah, that you have come across in the lecture most of the time, and turbine, yeah, vortex shading, ultrasonic, magnetic, thermal mass, pyrolysis, and target. Yeah. Some of you probably will be wondering how turbine can use to measure flow. Yeah. Um, any idea when a turbine being used to measure a flow? Normally we're talking about turbine. Actually, we're talking about producing power from the turbine. But now we say that we use turbine to measure the flow. Any idea? Can you give me an example of a turbine flow meter? Any idea? In a pipe, um, not really. In a pipe, then the pipe actually will disturb the flow. Yes, it can measure a strong flow. So in other words, actually turbine flow meter being used to measure things like current, for example. The turbine, the dam being used to produce a power, but turbine flow meter normally being used to measure a strong flow, like the stream flow actually. That's why when I asked you to do the Pulau Tiso project, yeah, what I have in mind actually the turbine flow meter. Yeah. Let me show to you because we still have ample of time. Let me show you the report that I have done for Pulau Tiso 10 years ago where we use a turbine flow meter. Yeah. You can see my desktop, right? You can see the desktop. Yeah. Okay. I go to okay. This is actually. Can you see that? Um. Okay. This is a ship actually at Pulau Tiso. And this ship belongs to Marine Department. This is what they did in 2010. So 10 years ago. Yeah. Okay. Can you see the one? Can you see the one? Yeah. So this is the current meter. Yeah, we look at the slot of that. So this is like Kaplan turbine. Yeah, this is like Kaplan turbine. Yeah. So they need to hook the turbine to a heavy weight. So you go down all to the bottom of the river or to the sea basically. Yeah. So this is the sea. Yeah. Pulau there is Pulau Triso at the back there. Can you see there? That's Pulau Triso at the back. Yeah. So this is how it looks like. Not that big. Basically about maybe 2 feet in space. Yeah. And they call it the current meter. Yeah, which is a turbine type. Um, I think this is the brand Bellport. That's how they do it. Okay. So they do measurements there. Yeah. So your estimate actually something that we have done 10 years ago. And then I reflect back. Um, we asked you to do something like that. Yeah. Okay. Um, then more interesting. So that's all. Yeah. Um, we're talking about the speed of tidal stream. Yeah. So the measurement not available. So we asked the Marine Department of Sarawak to do the measurement of the stream flow there. Yeah, so that we can see what kind of flow there. Yeah. This one here. So this is the flow meter, turbine flow meter they use to measure the stream velocity. Yeah. As a function of height of the water from the surface to the bottom. Yeah. So they took about 2 weeks to do these measurements, yeah, along the area. Yeah, but they park the boat there, or it's a ship actually, like a ferry, and then they put it down and they take the measurement. In this case, yeah. Okay. So this is we work together with Sarawak Energy, the Green Department or Jabatan Laut of Sarawak, and also Ministry of Public Utility of Sarawak. Yeah. So they did the measurement for us. Yeah. Okay, so any I see. So there is basically this is the turbine is now is connected to the computer, or in this case is the laptop. Yeah. So this is how it looks like. So basically what you all doing now. So do you think that the plot picture is something too easy? It's not because those taking the measurement have to stay there for 2 weeks on the ship for 2 weeks and do the measurements every um, yeah. So this already submerged in the water. Yeah. And this is one they want to submerge it down. Lottery so at the back there. Um, let's see. Let's see. Okay, so this is the measurement. For every 5 minutes interval, so they take the measurement. From there, they calculate the flow, um, the speed, and then from there they can calculate the kinetic energy flux density. How the measurement provide. This is the measurement that they have. Yeah, on one day alone. Yeah, the range for one day. Yeah, so almost 30% or 30% of the time the velocity around 0.5 to 1 per second. Okay, that is for the measurements, yeah, and how to use um, the measurement for 50, the total is the 50 for 50 hours. Yeah? Okay. Okay. Can I just open back? Okay, we go back to our PowerPoint presentations. Can you see the control systems PowerPoint? Yeah. Okay. I go back there again because I lost it in the content. So there is actually the flow meter by using turbine. Yeah. So other things like vortex shading, ultrasonic, magnetic, thermal mass, fluorescence, and target. So with that one you can Google out to know what type of flow flow meter is that. Yeah. And next actually the pressure. Yeah. For pressure we have a liquid column, um, elastic element, which is normally made of Borden tube or bellows and diaphragm. Yeah. Pressure can also measured by using strain gauge and piezoresistive transducer as well as a piezoelectric transducer and optical fiber. Yeah. So I also not very familiar with this. Maybe you can Google out what is actually meant with optical fiber, for example. Yeah. But for elastic element, I think we should be familiar with Borden tube, bellows, and diaphragm because this is being done in your lab 1 or lab 2 maybe, for fluid mechanics. And then for level, so from temperature, flow, pressure, we move to next one is level. So for level, we have flood activated, which is using change gauge or lever or magnetically coupled uh, flood activated. And for head devices, we have a bubble tube, and we also have electrical conductivity and radiations as well as radar. Yeah? For compositions, yeah, this is the applied measurements. You can have gas liquid chromatography or GLC, mass spectrometry, magnetic resonance analysis, infrared spectroscopy, Raman spectroscopy, yeah, ultraviolet spectroscopy, thermal conductivity, yeah, that's the applied measurement. Um, Refractive index can also be used to measure um, size, for example. For example, if I recall back when I did a measurement on the size of droplets in a spray, yeah, we use a laser to hit it on the droplets that flying through the air, yeah, and we put three sensors, optical sensors, to capture the refractive index from these droplets. So from that three sensors that measure the refractive index, we can derive the size of the droplet, yeah, from from uh, uh, from less than 1 millimeter, talking about the size from maybe few hundred um, micrometer or micron to maybe 10 micron, yeah, or 10 micrometer, for example. So we use the refractive index with that. And when we have more than two sensors, we have three sensors. Not only we can measure the size, but also we can measure the velocity of the droplets as it pass through the space where that laser light being shot to that particular area. Yeah, so we can measure the size of the droplets, velocity of the droplets as it pass by, as well as the directions of that droplets moving within that particular space, to the left or to the right on the axis, for example. And other compositions sensors or instruments, we're talking about capacitance probe, surface acoustic wave, electrophoresis, electrochemical, paramagnetic, which I also not very sure what are they, but you can Google it out. Chemi or bioluminescence, as well as a tunable diode laser absorption. So there are many types of instruments to measure compositions of a different property. Yeah. For example, the first one, gas liquid chromatography, basically to know what is the uh, component of the gas or the liquid. And mass spectrometry to measure the weight or the mass of the instrument. So now the questions will be, I'm not very sure whether Dr. Fikri already discussed with you on this, but when we're talking about instrumentation and control systems, one of the most important thing I think for you to consider um, the selections criteria for that particular instrument. Yeah. So just now you have seen there are so many instruments, right? So for example, even to measure the flow, for example, yeah. For example, the water stream, for example. How do you know that you should choose a turbine flow meter, for example, not a orifice or venturi or rotameter in this case, although they can do this, the job as well. Yeah. So one of the reasons is usually you need to know what are you measured. Yeah. Are you measured, for example, the velocity of a gas or a liquid, for example, yeah, or the temperature of a gas or liquid or a solid maybe. And at the same time also, once you know the medium, you need to know whether this gas or liquid are corrosive or not. They are corrosive fluid. Now, fluid consists of gas or liquid. Yeah, so they're corrosive or not. So let's say if you are measured um, and the temperature in a corrosive environment. So in this case, you cannot use a instrument made up of steel, but probably you need to choose an instrument made up of stainless steel because we can withstand the corrosive nature of that fluid. Yeah. The next will be the nature of the signal as well as speed of response. Yeah. So you want to have a measurement instantly. Yeah, that is connected to a computer where you need to make a decision straight away. In this case, you need something that is very fast. Yeah. So in this case, you need ideally you want to connect it to a by a wire to a system. Yeah. Um, or now even better by using a Wi-Fi or Bluetooth maybe. Depends on the distance whether it's, the signal can be transmitted within that distance or not. Um, Next will be the accuracy and also the measurement range. So just now we look at the example of the temperature. You should measure a water temperature, yeah, and you know that water temperature when it's boiling is 100 degrees Celsius. Yeah? So in this case, you probably your measurement target probably between 0 to 110 maybe. Yeah, not need to be until 1000 degrees Celsius if you know that the temperature of the water will not of the boiling water will not go more than 100 degrees Celsius, for example. The fourth thing still you need to consider also the cost. Yeah, the cost of the instrument, whether it's you can afford it or not. Yeah, whether your budget allow it or not. Yeah. So just now I showed you the turbine flow meter. Yeah. So you can imagine each of the turbine flow meter costs a few thousand US dollar. Yeah. So if you look at that picture of the turbine flow meters now, you can see that they've been secured with two things. One is the chain link. The one next is also a thread, a nylon thread. Why? Because the measurements of the water stream is um, the water stream can be very rough. Yeah. So if the chain snap, for example, at least we can have the rope to secure um, the turbine flow meter in case it drops in the sea, for example. Yeah. Um, Talking about the probably the depth of um, a few meters, yeah, and then murky water, it's not easy for you to locate it just like that. Yeah? So you need to secure it accordingly. So the cost is important, and then the previous plant practice, if you in a plant in a factory, you need to know what kind of instrument before, so that you can when you replace it, basically you know what kind of instruments you need to use, and the available space also important. Yeah. Imagine you want to measure the temperature inside a burner, for example, of uh, uh, hot flue gas inside a burner, for example. Yeah, it's not possible to use a thermometer. Differently, even the thermocouple also you need to be very specific which one you want to use. Yeah? But most importantly, actually, how you want to place this instrument inside that space. Yeah. So in this case, most of the plant will not put thermocouple or even thermometer in that kind of burner, but instead they check on the color of the flame. Yeah? So the color of the flame will give them uh, the range of the temperature being measured. Next will be the maintenance and the reliability of the instrument, also very important. If you need to calibrate it often, for example, yeah? So you need to have something that is easily maintained and reliable. Yeah. Materials of construction. Yeah? So this is uh, need to do also with the corrosive nature of the fluid that you want to measure, perhaps. Yeah. Invasive and non-invasive is also important. Imagine you want to measure the flow inside a small capillary, for example. If you put the instrument inside that capillary, your instrument basically block the flow, so you will not be able to get an accurate measurement. Yeah, so just now when I asked you, oh, what kind of flow that turbine can measure, a turbine flow can measure, so he mentioned pipe. It's not possible because basically the turbine inside a pipe already block the flow inside the pipe. Yeah, so basically overcoming the um, the frictions by the pipe by the turbine inside the pipe. Yeah, basically affect, you are basically affected the flow. Yeah, so basically it's not an invasive measurement, so it's not possible if you want to know the velocity of the free flow inside the pipe. Yeah? So in this case, probably you need to have a non-invasive type of measurement to measure a flow inside a pipe. Yeah, or maybe by using a Doppler, for example, or something that is not in contact with the flow. Yeah. Um, yeah. Uh, Another example probably talking about to measure the flow inside your blood pressure, blood vessels, for example, yeah, in artery, things like that. So it's not possible to put an instrument inside your artery, for example, in order to measure your blood flow, for example. Yeah. Yes, if you have a non-invasive, yeah, maybe talking about some dye, maybe so from the movement of the dye, DYE. You can basically know the flow inside the kind of small capillary or inside your blood artery. Yeah? And then the other uh, considerations will be with regards to environmental and safety aspect. Yeah? Whether it's in enclosure or it could be a fugitive emissions. But it means that when you want to measure something in an enclosed, something enclosed, for example, yeah? You cannot just simply go into the inside a tank, for example, and do the measurement. Yeah? Especially in a very um, dangerous environment, inside a oil tank, for example. Yeah? You many ending up being suffocated by that. Yeah? So in this case, you need something that is safe to use to do the measurements, yeah? And also environmental friendly in this case. So some of the um, work you need to do before you do a measurement with your instrument. You are no doubt that although your instrument is very expensive, up to date, and reliable, but as an engineer in a technical field, for any measurement you must do a calibration. So this is examples of temperature measurements, calibrations. Yeah. So you need to have a calibration. When talking about calibrations, basically you have the error, yeah, hysteresis error, random error, um, standard error, etc. Yeah. But before we do that, maybe you can go back to what you have learned about transfer functions before. Yeah. For example, if you want to measure uh, uh, measurements, yeah, and then probably they have a different instrument that being used. So in this case, they are in two series. In this case, we have two, basically two um, transfer functions. We're ending up with two transfer functions. Yeah. As I mentioned here, that you may need additional transducer for GM if its input is in milliampere or PSI. In the above case, DC is the dimensionless or volts. Yeah. So you have to convert it from one value from a physical to electrical value. You're actually ending up having two transfer functions for that particular transducer. So now go back to the calibrations work just now. What it means is when you do calibrations, you need to take into account the non-linearity issue. Yes, for example, if you want to do a measurement using a string, for example, going down is probably straight like that, ideal. But actually, we're going back. By going back again, actually it's not straight line like that. So you need when you do a measurement using string, for example, you need to calibrate it. Yeah, expansion, the higher expanded and retract, for example. Yeah, and then in calibration also you have what's called calibrations error, dead zone, threshold sensitivity. Yeah, as a given here. Yeah, you might have measurement like this y equal to mu plus b, but actually we come actually talking from here instead of here. For example. And then we have the what's called the repeatability and hysteresis errors. Yeah. So from measurement from here up, going up that way, but we're going back again. It's not really using the same path, but on different path. So you need to consider that. So you have a certain percentage of error in your measurement. So that is what I mean with calibrations in this case. Yeah. So the blood evening with hysteresis is the A is the hysteresis. Yeah. So going up this way, but going back different way. Or that band basically going up this way, but going down at a certain value minus, for example. Yeah. And what it means with gain of a non-linear transistor as a function of operating point. Yeah. So we have operating point 1 and operating point 2 here. Yeah. So the gain Km1, Km, K measurement 1, K again, K measurement 2, for example. In this case here. And analysis of type of error for a flow instruments, this range is 0 to 4 flow units, for example. So for a true value to the most likely measured value, we have a total error, the maximum total error, which consists of systematic error or bias and random error in terms of repeatability. Yeah. So that's why in any instrumentation, when you do a measurement, any experiment, you need to repeat it at least 3 times or even better 4 times or more so that you can get the average. Yeah. And also the mean or the median of that average actually give you um, the, 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 the percentage of error which is the total error consists of the systematic error and the random error in this case. So some examples like measurement of temperature using thermocouple, for example. Yeah. So one example. So from there you can calculate the transfer functions. Yeah. So there are, for example, the lags or time delay due to pneumatic transmission lines, for example. Yeah. So one is the things that lead to lags or time delay. And for this one, if we got the pneumatic valve, yeah, we do A. Yeah. So there again, there some reasons for time delay or lag in this case. Yeah. So we look into some of the diagrams here. Yeah. So control valve characteristics, we have this is what you expect. but there's some error in going up and going down. Yeah, and when you're talking about the pressure vessels, for example, so there are many um, components here. We have pump, or maybe heat exchanger. We're talking about the temperature change control valve to protect the pressure vessels, for example. The pressure inside the pressure vessel, for example. Yeah. So there are few parameters involved. Yeah. Yeah, so this is a control valve in series. We have pump and a heat exchanger where the pump discharge pressure is constant. Yeah. So expected to be able to derive in this case what is the um, mathematical model for the pump, mathematical model for heat exchanger. Yeah, so you need to know what is the heat exchanger in this case before you can come up with the transfer function for all these systems. Any questions so far? Already 3 o'clock. Already with you for 1 hour. Any questions? Okay. So ideally, you need to know something that is normally that we come across very often in mechanical engineering. Pump, for example, you need to know how pump is work. Heat exchanger, you learn about thermodynamics. So you need to know what is how heat exchanger work. Um, and eventually, you need to know what is the numerical model for a pump, numerical model for heat exchanger, etc. Yeah. Any question? Remember, this is my last week giving a lecture. So next week you'll be with Dr. Fikri if we decided to meet you all online. Otherwise, you will straight away do your assignment in week 14 in 2 weeks time. 20th of July. Dr. Fikri will post the question. Questions? So for this example, this one here, yeah. Suppose that the valve has linear trim and flow must be increased. Then the change in pressure delta P through exchanger did not change and valve will behave linearly. That is true for low flow rates and since it takes most of the delta P and for higher flow rates delta P through exchanger will be important. So changing effective valve characteristics. Yeah. So the valve must open more than expected to produce a non-linear behavior. Then the equal percentage in this case behave more like linear valve. Yeah. So for size of a change in the pressure uh, in the valve is 20%, the total W is at least S is equal to 50%. Yeah. So in this case, the valve needs to operate between 5% and 95%. So the flow is the square root of the change in the pressure in the valve. Yeah. So this is the valve characteristics in this case. For example, the one is now, this one. Yeah. Okay. What it means with pneumatic control valve. So this one we look into a different type of pressure measurement. So this is the schematic of a pneumatic control valve. You can see here. There's an input signal. Go to the diaphragm here. Actuator spring and valve positions indicator, valve plug stem, and the valve body, the valve plug, and valve seat. So if high, so if this valve plug go down, so there's no flow. Yeah. If it up, then there'll be a flow. Yeah, see the flow direction from left to right in this case. Any questions? I think you have seen this kind of diagram when you do your lab 1 or lab 2 last time, right? So this is probably a mere revisions or probably something for you to re-emphasize what you have learned in your beginning lab 1 and 2. Right? So in this case, if you want to uh, uh, maintain the instruments to work in order, yeah, to avoid failure, you need to keep process pressure low, protect the environment of human engineers, yeah, and the pneumatic control valve are to be specified for the applications listed below, which is steam pressure in a reactor coil, flow rate of reactants in polymerization reactor, flow of effluent from wastewater treatment holding tank to a river, so the environment, and flow of cooling water to a distillation condenser, talking about the heat exchanger. So you learn about heat exchanger in thermodynamics, correct? You learn about heat exchanger in thermodynamics, is that right?
Yes.
So in this case, you know how a heat exchanger is working, yeah? With their distillations, condenser, etc. Yeah? So that's the end of the lecture on control system instrumentation. So you can say this is an application of instruments in control systems. Yeah, talking about heat exchanger in this case. Any questions?
No, no questions.
No questions. If no questions,
No.
then um, I wish you all the best. So um, if you need a quick revision, I can give you a quick revision this Friday. Yeah, for 1 hour. After that, next week, and Dr. Fikri will do another revision for you if he thinks it's necessary. I will let him know. I will inform Dr. Fikri that this is will be my last week having lecture with you, and next week he can take over. And this coming Friday, I probably will have a short class with you from 10 to 11, yeah, just to cover what we have discussed so far. By week 14, you can start to do your assignment. Yeah. Any questions? Okay, if no questions, if you want to check your attendance again, I can click on the here. Okay, so if you have no questions, you can leave the meeting. But if you have any more questions, I can stay here for another 5 minutes to take your questions until 3:15. Yeah?